Welcome to this video on how to calculate work done by a variable force.
We can start by describing how to calculate the work done by a constant force. When a body is moved a distance d along a straight line as a result of being acted on by a force of constant magnitude F in the direction of motion, we can calculate the work W done by the force on the body as W is equal to F multiplied by D. For example, if we have a force F equal to 8 newtons acting on a body, and as a result of that force, that body moves a distance d equal to 3 meters, we can calculate the work W done by that force on that body as 8 multiplied by 3, giving us 24. And for our units, we have newtons multiplied by meters, giving us Newton meters. This combination of units comes up regularly and has its own special unit called the joule, which we represent with a capital letter J. We can say that this force did 24 joules of work on the body.
We're now going to describe how to calculate the work done by a variable force along a straight line. When we apply a force that does not have a constant magnitude, we cannot use the previous formula alone to calculate the work done. We can account for variation in the magnitude of the force by using an integral formula instead. When the force is acting along a straight line, we can represent that line with the x-axis of a graph. To calculate the work done by a variable force, we want to find a continuous function f of x, which returns the magnitude of the force F as a function of its position on the x-axis. Shown now on the right-hand side of the screen is a plot of a function of this type. Here we have a plot of the function f of x is equal to x squared. On the y-axis, we have the force F in newtons, and on the x-axis, we have the distance x in meters. So, for example, at a distance of x is equal to 2 meters, the force is equal to 2 squared, which is equal to 4 newtons. Using this function, we can then calculate the work W done by the force F of x on the body along the line from x is equal to A to x is equal to B as W is equal to the integral from A to B of f of x dx. So, for example, if we wanted to calculate the work done by the force on the body from x is equal to 0 to x is equal to 3, we'd set our lower limit of integration a to be equal to 0, and we'd set our upper limit of integration b to be equal to 3. We'd then set our function f of x to be equal to x squared, and then by evaluating this integral, this would give us the work done by the force on the body from x is equal to 0 to x is equal to 3. Now, that value would be equal to the area underneath our function curve from x is equal to 0 to x is equal to 3. What we're going to do for our next section is we're going to explain the theory behind this calculation.
In our example, shown to the right, the force F doesn't have a constant value over the closed interval from x is equal to 0 to x is equal to 3 meters. When we refer to the closed interval from x is equal to 0 to x is equal to 3, we're referring to all of the points between x is equal to 0 and x is equal to 3, as well as the points x is equal to 0 and x is equal to 3. Because our force F doesn't have a constant value, we cannot just use our constant force formula alone to calculate the work done over that closed interval. What we can do instead is, we can divide the interval into n sub-intervals. What this means is that we take our closed interval from x is equal to 0 to x is equal to 3, and we divide that up into a number of smaller intervals, which we call sub-intervals. The variable n, that's equal to the number of sub-intervals. For this example, we're going to use 3 sub-intervals. So our variable n, that's going to be equal to 3. Shown now at the right-hand side of the screen, our first sub-interval is currently being highlighted in red. And we're going to use the variable delta x1 to represent the length of this first sub-interval. Shown now at the right of the screen, our second sub-interval is currently being highlighted in red. And we're going to use the variable delta x2 to represent the length of this second sub-interval. And shown now at the right of the screen, our third sub-interval is currently being highlighted in red. And we're going to use the variable delta x3 to represent the length of this third sub-interval. If we choose a point x inside the first sub-interval and call that point x is equal to c1, we can calculate the force F at that point as F of c1. We can estimate the work done over that first sub-interval as the force F of c1 multiplied by the distance delta x1. Now, this value of work is equal to the area currently shown highlighted in green to the right. We can repeat this process for the other sub-intervals. We can choose a point x inside the second sub-interval, call that point x is equal to c2, and we can calculate the force F at that point as F of c2. We can estimate the work done over that second sub-interval as the force F of c2 multiplied by the distance delta x2. That value of work is equal to the area currently highlighted in green and outlined in red as shown to the right. And we can choose a point x inside the third sub-interval, call that point x is equal to c3, and we can calculate the force F at that point as F of c3. We can estimate the work done over that third sub-interval as the force F of c3 multiplied by the distance delta x3. This value of work is equal to the area currently highlighted in green and outlined in red shown to the right. We can estimate the total work done over the interval from x is equal to 0 to x is equal to 3 meters as the sum of the work done over all of the subintervals. This type of sum is referred to as a Riemann sum, and we can represent it as the sum from k is equal to 1 to k is equal to n of f of ck delta xk. This is a Riemann sum expressed using sigma notation. We're going to explain these terms now. These terms, highlighted in red, represent the sum from k is equal to 1 to k is equal to n of the terms that follow. The variable n is equal to the number of subintervals. In our current example, n is equal to 3.
This Riemann sum, written in sigma notation, is a shorter way of representing the following. It's equal to f of c1 times delta x1 plus f of c2 times delta x2 plus f of c3 times delta x3, where f of c1 times delta x1, that's equal to the force F at c1 multiplied by the distance delta x1, where that product gives a value of work equal to the area shown highlighted in red to the right of the screen. Our f of c2 times delta x2, that's equal to the force at c2 multiplied by the distance delta x2, which gives a value of work which is equal to the area shown highlighted to the right of the screen now. And f of c3 times delta x3, that's equal to the force F at c3 multiplied by the distance delta x3. This product gives a value of work equal to the area as shown to the right of the screen, highlighted in red now. This sum is an estimate of the total work done over the interval from x is equal to 0 to x is equal to 3. We can create a Riemann sum using a larger number of subintervals with smaller subinterval lengths. This will now be shown to the right of the screen. As the subinterval lengths get smaller, we expect the accuracy of our estimate to improve. As the subinterval lengths get smaller, the value of force across a subinterval approaches a constant value. As this happens, the one value of force we choose per subinterval better represents the force across the subinterval. So, as the subinterval lengths get smaller, we expect the accuracy of our estimate to improve. The limit of the Riemann sum as the longest subinterval length approaches 0 is the value that the sum approaches as the longest subinterval length approaches 0. This limit can be represented using the terms shown below. We're going to explain these terms now. These terms, currently shown highlighted in red, represent the limit as the longest subinterval length approaches 0 of the terms that follow. If you haven't seen this variable before, currently highlighted in red, this capital P between a pair of parallel lines, this represents the norm of the partition, which is equal to the longest subinterval length of our Riemann sum. So these terms, currently shown highlighted, represent the limit as the longest subinterval length approaches 0 of the terms that follow. Altogether, these terms represent the limit of the Riemann sum as the longest subinterval length approaches 0. The limit of the Riemann sum as the longest subinterval length approaches 0 is the definition of the definite integral of the function over the interval from x is equal to a to x is equal to b, where in our example a is equal to 0 and b is equal to 3. This definite integral is also equal to the area underneath the curve on that interval from x is equal to 0 to x is equal to 3. We define the work W done by a variable force f of x directed along the x-axis from x is equal to a to x is equal to b to be equal to the integral from a to b of f of x dx.